We set sail on this new sea because there is new knowledge to be gained and new rights to be won, and they must be won and used for the progress of all people. For space science, like nuclear science and all technology, has no conscience of its own. Whether it will become a force for good or ill depends on man. And only if the United States occupies a position of preeminence can we help decide whether this new ocean will be a sea of peace or a new terrifying theater of war. I do not say that we should or will go unprotected against the hostile misuse of space any more than we go unprotected against the hostile use of land or sea. But I do say that space can be explored and mastered without feeding the fires of war, without repeating the mistakes that man has made in extending his writ around this globe of ours.
Ladies and gentlemen, please welcome Alan Price, Director of the John F. Kennedy Presidential Library and Museum.
Thank you. As you heard, I'm Alan Price, Director of the John F. Kennedy Presidential Library and Museum, and just thrilled to have you here with us this afternoon. This is an extraordinary celebration of the moonshot and the Apollo 11 mission that changed history. I'd like to begin the afternoon by extending my sincere gratitude to Raytheon, the lead sponsor of today's Space Summit, for their partnership in helping us tell the story of the first moon landing, not just today, but throughout this anniversary year. We're grateful for Raytheon's support in enabling us to explore what the moonshot has to teach us 50 years later about science, technology, and the capacity for human achievement. Boeing has also sponsored today's program, and we are grateful that they share our commitment to honor the past so we can look to the future. I also want to thank the following sponsors for their support of our mission and programming: Draper, Bank of America, the Lowell Institute, Gourmet Hospitality Group, Vertex Pharmaceuticals, National Geographic, WBUR, the Boston Globe, and Xfinity. We would not be here today without Ambassador Caroline Kennedy, whose vision, imagination, and tireless efforts have made this day possible. Caroline has been instrumental in putting together today's program, and we're profoundly grateful for her indispensable leadership. I also want to thank Ed Schlossberg for his leadership at the Kennedy Library Foundation and his enduring commitment to ensuring that the Kennedy Library and its programs are meaningful and accessible to new generations and new audiences both here in Boston and around the globe. I extend my sincere thanks to Jack Schlossberg and Tatiana Schlossberg for everything they do on behalf of this institution day in and day out, year in and year out, to carry forward President Kennedy's extraordinary legacy. I also want to recognize the Honorable Patrick Kennedy, Stephen Kennedy Smith, and Cheryl Buchanan, Matt and Kate Kennedy. Finally, I want to extend a special welcome to all the panelists who have been contributing to our programs throughout the day. We're thrilled that you're here with us. As was said earlier, it's amazing to interact with one astronaut, to have 5 astronauts and former astronauts and NASA administrators and NASA historians all together. I hope this inspires a new generation to be astronauts and engineers and historians. Thank you for being here with us today. And now it is my pleasure to introduce Dr. Michael Freilich, who until very recently was NASA's Earth Science Division Director. Through the use of satellites and other instruments in space, Dr. Freilich's research has deepened our understanding of the Earth's air and water, the defining elements of our environment. He is an oceanographer, an educator, an administrator, and an innovator. And we're honored to have him with us today. Ladies and gentlemen, please welcome Dr. Michael Freilich.
Very much. Well, thank you very much for coming. President Kennedy inspired us and challenged us to look upward and to reach the moon. Continuously, throughout the nearly 6 decades since he made that clarion call, NASA, the agency that he empowered, our nation, and indeed all of humanity, have used the vantage point of space to also look downward and to explore and understand as never before our home planet. Let me start by saying what I think are perhaps the most profound 4 words in the English language. The climate is changing. Profound because it is having a profound impact on our globe. Lakes and inland seas with warming temperatures and human use are drying. Get this to work here. The poles, both the Arctic and the Antarctic, are changing perhaps more rapidly and more sensitively than other places. Here you can see comparisons between April of 2013 and April of 2018 for sea ice in the Bering Strait. It was there, it's not there any longer. Glaciers are retreating substantially. Sea level is rising, and we'll have more to say about that later on. You can see here differences in our coastline between today and 1 meter sea level rise and 3 meter sea level rise. If you live in southern Florida, on the Gulf Coast, even on the east coast of the United States, sea level will have a tremendous impact. Changing sea level will have a tremendous impact on you. And this is not a theoretical problem. Today, in Miami during spring tides, the storm sewers sometimes run in the opposite direction, bringing water up. In Venice, from September to April, they actually provide flooding forecasts based on tides and weather. And sea level change is having an impact on all of us. The climate is changing. It's profound. Humans are the only species that can change what we are doing now and into the future based on our projections of what we do and how it will impact generations to come. No other living being that we're aware of can think generations ahead. So that presents us as a species with a profound responsibility to future generations. You can see here in the next few slides some impacts on our land surface and in our environment of clear human activities. These are the Suderman glaciers in New Guinea, the most tropical glaciers in the world. They're at altitudes of about 16,000 feet, 4,800, 4,900 meters. You can see that from 1998 to 2017, they have virtually disappeared. Equally of interest from this Landsat set of images is this thing, which is the world's largest gold mine and second largest copper mine, the Grasberg mines, which did not exist in 1998. Our urban areas are expanding. This is Las Vegas. What started in Las Vegas doesn't apparently stay in Las Vegas. And if you actually look carefully, you can see that Lake Mead was larger when there were fewer people, and it's smaller and actually much smaller now when there are more people. Whoops. It's not just in the United States. Shanghai, China, in 30 years or so, has expanded by approximately a factor of 4 in population. We are changing the cover of the Earth and therefore its environment. On a much smaller scale, from Dubai, Landsat imagery from space, you can see that planned development has made land where there was no land before, the Palm Islands, Dubai in the United Arab Emirates. But we can change the evolution of our environment. The greatest uncertainty in how the Earth will evolve over the next several centuries is not our lack of understanding of processes. The greatest uncertainty is what policy decisions humans will make, nationally and internationally. In late 1970s, early 1980s, the nations of the world got together and, having discovered the existence of the stratospheric ozone hole, came up with the mechanism and the response through the Montreal Protocols. And in fact, globally, we have changed the chemicals that we use so that the chemicals that we're using now are less deleterious to the stratospheric ozone. And indeed, what you can see here is that from the time the Montreal Protocols were put into effect until now, the measurements of the size of the ozone hole, it has gotten larger as predicted by the black line model. But in the coming years, the size of the ozone hole is expected to generally decrease until around 2070 or so. It will be at the same small size as it was when Ambassador Kennedy and I were growing up, and maybe some of you. We can change how the environment evolves. I might also point out that the new chemicals that we're using that preserve ozone have about 10 times the global warming potential of the old ones. So some problems are solved, some are not. Humans are putting fossil fuel carbon into the atmosphere. We are liberating it from its underground reservoirs where it was sequestered, and it is going into the atmosphere. About half of what we put into the atmosphere each year stays there from fossil fuel burning. The other half apparently goes into the ocean. And you can see that relentlessly, this is from in situ measurements on land, year by year by year, the so-called pump handle chart, carbon dioxide levels in the atmosphere are increasing, differently in the north than in the south because of the different distributions of population and land mass and seasonality. Our Earth is a complex place. Processes are happening in the ocean, in the atmosphere, on the land. The climate is changing is profound. The fact that we know that the climate is changing, and we know with certainty and precision and accuracy, is a profound testament to our technological abilities, as President Kennedy pointed out. It is the vantage point of space that has allowed us to make measurements of many different processes, all at the same time, with high spatial resolution, but global coverage, frequently over long periods of time, that allow us to understand the connections in this, our complex home planet. Only from the vantage point of space can we do that. We make measurements and observe the Earth from many different places in space. This is an image from the Cassini mission at Saturn, a rather dramatic, aesthetically beautiful planet, and a tiny blue dot, which if you look more carefully is two dots, one of them blue, one of them gray, the Earth and the Moon. Cameras that we put on spacecraft can image the Earth from the farthest regions of the solar system, more than 1 billion kilometers away. We are making measurements of the Earth today from satellites, one in particular called Discover, that are about 1 million miles away in a stable orbit called the Lagrange 1 orbit, the Lagrange 1 point. This is an orbit that allows the satellite to always remain on the line between the Earth and the Sun. So it's always seeing the full disk of the Earth. I call it the Earth at noon. We can make measurements and see evolution of weather and seasonal evolution that way. Of course, if you're 1 million miles away from Earth, 1.5 million kilometers, you're outside the Moon's orbit. So every now and then, at times that the Greeks could have predicted for us, the Moon comes between the Earth and the satellite. And that's what you're seeing here. And so the side of the Moon that's being imaged is the side of the Moon that's away from the Earth. The side we don't see. The side we call the dark side of the Moon. That's the side of the Moon that faces the Sun. You figured that one out. Most of our measurements come from satellites that are orbiting much closer to the Earth, from a couple of 100 miles or 400 or so kilometers up through 1,000 or 1,600 kilometers or so. And NASA research missions, not counting research missions from many other agencies, are constantly orbiting the Earth, making these measurements. High resolution global coverage, frequently everywhere, over long periods of time, many different variables. And you can see that these spacecraft that are orbiting are not orbiting randomly. Some of them are in constellations, etc. This is sort of a flat view of the NASA research satellites. The ones on the bottom are on orbit right now, more than 20 of them. The ones on the top, in sort of that orange and the pukey yellow, are under development for launch in the next couple of years. We have many different instruments and satellites making measurements of many different quantities. By exchanging the data between missions, between agencies, and between countries, scientists and others can understand the connections between processes, not just the individual processes that are taking place on the Earth. You can also see that, as you heard this morning, we are using the International Space Station as a satellite to hang instruments on to measure the planet from which it came. And we are pushing the bounds of technology with scientific and technology development satellites on, or instruments on, and payloads on CubeSats and smallsats. We're making measurements, as I said, of many different quantities. You saw the pump handle diagram of CO2, carbon dioxide concentrations in the atmosphere from one of our NASA satellites, so-called Orbiting Carbon Observatory 2. We're watching the Earth breathe. Every 2 weeks, from the second half of May, it happened to be 2015 in this chart, all the way through the end of the summer, you can see the carbon dioxide levels in the atmosphere in the northern hemisphere changing. Carbon dioxide levels are high in the beginning of the spring after the winter, before photosynthesis has cut in the boreal forests, for instance, and the land masses in the northern hemisphere. And as time goes on, the actual natural processes scavenge that carbon dioxide out of the atmosphere. Concentrations are lower in the middle and end of the summer. We can make these measurements with resolution and with precision. What I'd now like to do is take us on a quick tour of measurements of what scientists call the hydrologic cycle, water on Earth. And this is sort of a cartoon which I put together for NASA administrators. Not Charlie, not Charlie. Charlie got it all. But they haven't all been as good as Charlie. Of the hydrologic cycle on the Earth. And you can see the reservoir. Whoops, sorry, didn't mean to do that. If we can go back. There you go, thanks. The reservoirs, such as in the ocean, in the groundwater, lakes and rivers. You can see the fluxes, that is the exchanges between the land and the atmosphere, and the ocean and the atmosphere. We can measure from space, and we are measuring from space, virtually every part of the hydrologic cycle. A tremendous technological feat. We are measuring sea level using instruments called precision altimeters mounted on satellites that are orbiting 1,600 kilometers above, about 1,000 miles above the Earth's surface. And these are incredibly precise measurements. Precisions of about 1 part in 10 to the 8th. From that high, we can make measurements, we can detect changes in global ocean sea level on the order of a couple of centimeters. Okay? To give you an idea, if we were to take one of these instruments and adapt it somehow so that it's still measured 1 part in 10 to the 8th and flew it on an airliner, it would be able to detect a dime lying flat on the surface from 40,000 feet. That would be an easy detection. And what you can see is that virtually monotonically, relentlessly, sea level globally averaged is rising. And it's rising at about 3 millimeters per year globally average. Some places it's happening faster. Some places it's happening slower. But if anybody says to you, we're not sure the climate is changing, you can simply say, why is sea level rising decade after decade? And these are measurements, by the way, that NASA and the French Space Agency and now the European Space Agency and others are making. But it's not enough to just measure the Earth. We need to understand it as well. And in addition to flying the altimeters that measure global sea level, we are also flying instruments and spacecraft that measure gravity. And in fact, Maria is probably going to make a mention or two of using this same technology to measure gravity on the moon. We're using it to measure gravitational changes on the Earth, precision gravity measurements. It's a really hard measurement to make. You take 2 spacecraft and you fly them a couple of 100 kilometers apart, and you very, very precisely, like to the width of a human hair, measure the difference in distance between them. And they speed up and slow down based on the local gravity under them. This way, we not only are measuring sea level, but we're measuring changes in mass, because that's what changes the gravity. And on Earth, the way you move mass around is by moving water around. And therefore, we know that although sea level is rising at 3 millimeters per year, we're only putting more water into the ocean to accommodate or to account for about 2 millimeters per year of that sea level rise. The remaining third is the result of heating of the upper ocean. You heat a liquid, it expands. That's what happens in your thermometer. You heat the upper ocean, and it expands and sea level rises. We not only know what's happening, we know why it's happening from the satellite measurements. We're measuring sea ice from satellites. What's shown here are two things. One of them is the area of sea ice. That's the black curve here in the Arctic, measured from satellites over 17 or 18 years, and we're continuing to make those measurements. We have about half the area of sea ice in January now that we had at the turn of the century. But perhaps even more importantly, we are measuring from the satellites the type of ice, and that's what each of these thumbnails is. The red in the thumbnails is thick, multi-year ice. The blue in the thumbnails is thin, first-year ice. You can see that there's much less multi-year ice now than there used to be. Who cares besides the scientists? We all care for the following reason. Thick, multi-year ice is controlled by ocean currents. But thin, first-year ice is controlled by how much sunlight reaches the ocean, that is, controlled sort of by cloudiness. It's the difference in modulating mechanisms, the shift from an oceanic modulation to an atmospheric modulation that can cause rapid changes in climate, the so-called tipping points. We're making those measurements from space. And when the sea ice goes away, you can think of sea ice as sort of acting like the cork in the champagne bottle for glaciers that drain the ice sheets in, say, Greenland or the Antarctic continent. All of these measurements of ice velocity were made from orbiting spacecraft. And you can see that the Antarctic continent is more or less draining towards the ocean. We're using those gravity measurements to also make measurements of the amount of water that's tied up in aquifers, subsurface water, excellent fresh water in general. You can see here over time in the Punjab region of India, where there's only 150 million people that live in this area, okay, that over time the levels of the aquifers have been draining for good reason. Okay, we're pumping the water out for people to drink, using it for irrigation, but we're doing that on a time scale of tens to 100 years, whereas it takes thousands of years to actually fill these aquifers. And using global analyses of the GRACE, the gravity measurements, which, by the way, are joint between NASA and Germany, scientists can actually track which aquifers around the world are filling and which aquifers around the world are draining. We are measuring rain globally. Ambassador Kennedy talked about it. She was there. She enabled the launch of the joint JAXA, Japanese Space Agency, NASA Global Precipitation Measurement Core Observatory. We're doing it with this NASA JAXA spacecraft and a host of other international spacecraft that were launched for different reasons, but which make measurements that can give information on global precipitation patterns. And here you can see the measurements from that so-called GPM spacecraft over time, and then all the other ones. I hope you don't get seasick, Laurie, take a pill. When you put all of those measurements together, whew, makes my head spin, we are now measuring for the first time on spatial scales of a couple of miles and temporal scales of less than a couple of hours, rainfall over the Earth. Before this, we did not have global rainfall measurements. I like to say that the only thing that we used to know about global rainfall before was wherever I and my family were going on vacation, it was going to rain then and there. These measurements, which I won't have time to go into in detail are telling us about the structures of storms and the mechanisms that control the intensity and the track of hurricanes, such as Hurricane Irma, shown here. The measurements that we take for science are being used for societal benefit. Here you can see a NOAA hurricane forecaster who said that based on, turned out to be a him, based on his analysis of a recent GPM overpass, he was changing the intensity of the storm, and he was noticing that, that there was an eye wall replacement taking place. He was quoting the NASA measurements to bolster his forecast. And by making measurements of things like rain on the bottom and soil moisture and sea surface saltiness, salinity on the top, we're again looking at connections between processes. For instance, if you look carefully here, you can see that when it rains in Australia, soil moisture goes up. It rains, it gets muddy. We didn't need satellites to understand that. But you can also see things like when it rains in the interior of the Amazon rainforest, then the Amazon floods, and this low salinity plume of nutrient-rich water goes into the western tropical Atlantic. This is important for ecosystem and ocean circulation studies. You can also watch the Mediterranean get saltier and saltier over the summer. So, by using the unique vantage point of space, looking down on our planet, we are understanding not only individual processes, but the connections between processes. Because this is the planet where all the people live, except for Palo's extraterrestrials on the ISS. We can develop societal benefit from our observations and our understanding. We are using the vantage point of space to understand our planet and to improve the lives of each and every human being on it. Thanks very much. And I think we're going to do questions afterwards.
Wow. Thank you, Michael. Again. And now it is my pleasure to introduce an all-star lineup of scientists who will talk us through some of the big questions about the universe that science and space exploration have enabled us to answer. Equally importantly, these distinguished leaders will help us to understand what we still don't know and why it's important. Dr. Laurie Leshin is a space scientist and the current president of Worcester Polytechnic Institute. Previously, she served as a senior leader at NASA, where she helped oversee implementation of dozens of science missions and all of NASA's future human spaceflight activities, including climate missions, space telescopes, and the rockets and capsules that will take astronauts to the International Space Station, the Moon, and Mars in the coming decades. She has so many accomplishments and honors to her credit that I can't list them all, but among the many, asteroid 4922 Leshin is named for her. You're going to see a theme in a moment. Professor Sara Seager is the class of 1941 professor of planetary science, professor of physics, and professor of aeronautics and astronautics at MIT. Her research focuses on the search for life beyond Earth by way of exoplanet atmospheric biosignature gases. Professor Seager is an international leader in the search for another planet Earth. directing major research initiatives for MIT and the Jet Propulsion Laboratory, among others. She was named a MacArthur Fellow in 2013, and she has so many accolades to her credit that once again I can't list them all, but among them she too has an asteroid named for her, asteroid 9729 Seager. Dr. Maria Zuber is the E.A. Griswold Professor of Geophysics and Vice President for Research at MIT, where she oversees MIT's Lincoln Laboratory and more than a dozen interdisciplinary research laboratories and centers. She also leads MIT's Plan for Action on Climate Change. Dr. Zuber's research bridges planetary geophysics and the technology of space-based laser and radio systems. Since 1990, she has held leadership roles associated with scientific experiments or instrumentation on 10 NASA missions. She is the first woman to lead a science department at MIT and the first to lead a NASA planetary mission. She too has numerous awards and honors to her credit, and it would not surprise you to learn that asteroid 6635 Zuber is named in her honor. This is going to be a thrilling hour of discussion, and if you leave today with more questions than you came in with, there's a good chance that one of the brilliant people on this stage will eventually discover the answers. We're delighted to have S.E. Cupp here to moderate this conversation, a graduate of Cornell University. Ms. Cupp has written for a wide variety of publications, including the Washington Post, the Daily Caller, Slate, and the American Spectator. She is currently the host of the weekly CNN program S.E. Cupp Unfiltered, which explores topical political news with policymakers, journalists, and other newsmakers. Please join me in giving a warm welcome to her and all of our distinguished panelists.
I want to start by thanking Alan and the JFK Library, as well as Ambassador Kennedy, for hosting this incredible event. I can't believe I'm getting to sit next to these incredible women as part of such an important commemoration of history. At CNN, there's a cupboard in the kitchen with a mug in it. It is named the S.E. Cupp mug. It's not an asteroid, but it's what I got. It's what I got. I'm really proud of it. I do politics, but I need to confess I am a space nerd, a frustrated one. I grew up with a red Tasco Halley's Comet series telescope that I used to look out of my window just 20 miles north of here in Andover, Massachusetts, where I grew up. I want to know what got all of you interested in space as girls. Do you want to start?
Sure, I'll start. Hi, everyone. Welcome. So nice to have you here with us today. For me, I was alive when Neil and Buzz took their historic steps on the moon 50 years ago next month, but I do not remember it. I was a little too young. For me, the first moment of awe was actually looking at pictures from the surface of Mars from the Viking landers, which landed in 1976. And I grew up in Phoenix, Arizona, and there was just something about that red desert landscape that spoke to me. I wanted to reach out and touch those rocks, and it's inspired me incredibly. And that was probably really the first thing. And then because we grew up in Arizona, my dad took us to the Grand Canyon as around that same time. And when we got there, there was a sign behind him that said, "Please don't take rocks from the Grand Canyon. You know, it's like a national park." And my dad said, "See, that's how the Grand Canyon formed. Everyone came, took a rock, and there you go." And I remember, even as a little kid, thinking, I don't think that's right. It was my first scientific hypothesis, I think, but very connected to the land, to the rocks, and those rocks from Mars still fascinate me today.
It's a great dad joke. Dr. Zuber.
Great. So for me, space exploration was genetically encoded. So there are actually legends in my family of me jumping up and down in my playpen, pointing at the television, like when the Geminis were in orbit. Not even the launches, which you could imagine for a baby, but the Geminis, and I would just watch it constantly. So actually, when I was in elementary school, I started reading high school textbooks, and I got a physics book, and I taught myself optics, and I started building my own telescopes, and
Me too.
I ground my own optics. I made my own eyepieces, and I just never stopped exploring.
Wow.
So.
Dr. Seager.
My story's a little more simple than that. When I was about 5 years old, my dad took me to a star party. And that's not like Hollywood stars or anything. That's where the amateur astronomers get together, even in the city, like here in Boston, and they have their telescopes. And I remember looking through the telescope and seeing the moon for the first time. It was like, wow, it is a whole other world out there. And I see a lot of school-age children here. Ask your parents or your teacher to take you to a star party so you can look through the telescope. Even from the city, you can see some amazing things.
I want to know, growing up, for each of you, were there women role models in space science, or were you surrounded by boys?
Not a lot, I will confess. For me, one of the ways that my sort of fascination with space as a young, I loved space, but it never actually occurred to me you could have a job working in the space program, to be honest. And when I was 19, an undergraduate at Arizona State University, Forrmer Devils, I saw an ad for summer interns at NASA. And I miraculously hadn't missed the deadline and that kind of thing. And so I actually pulled the whole thing off the wall, and I cold called one of the only women full professors of science, really, but she was an astronomer at ASU. And I'll never forget this. She physically dropped what she was doing. I knocked on her door and said, can I come in and ask you about this? I don't understand what this is, really. Can you help me? And she physically dropped what she was doing, and she said, come in, sit down, let's talk. And as a result of that conversation and a well-placed phone call, I ended up getting that summer internship at NASA, and that really was the lightning bolt for me. And I've never forgotten that, and we're all educators, we're all at universities, and I just don't think people realize that. I think it's what keeps us all going as educators, is that opportunity to fundamentally change the trajectory of a young person's life. And she was ended up being an amazing mentor.
Yeah, so I had no women role models because there were none to have, but fortunately, I was oblivious to this. And it's one of my great strengths, I think. Actually, the first Mars mission that I was on, I got a phone call from somebody in the press that said, I'm looking here, and there are 87 science investigators on this mission, and you're the only woman. And I went, no way.
Because you hadn't noticed.
And then I pulled up the file and opened it up, and I went, whoa, no wonder I get asked to give so many talks on this. I actually never had a female mentor until Susan Hockfield was named president of MIT, and I was the only woman department head in science or engineering, and when she was elected, I got a phone call from the corporation office that said, hey, this woman's going to need some friends. Would you talk to her? And so I, started talking, and it was the first time that I realized, wow, this is so fantastic to have this, inspirational woman to talk to.
She reached out to me when I first became college president here in Massachusetts. I didn't know her before either, and she's been fantastic as well.
Yeah.
It is an amazing thing.
It's important.
Yeah.
It is. Yeah, I didn't know a lot of women scientists until I came to MIT. Maria recruited me to come to MIT and be a professor there, and MIT is good at hiring and retaining women, actually. But as a child, like Maria, I was mostly oblivious. There were hardly any, I didn't have women role models. I didn't know other girls interested in science. But I think it's really about the mentors, my dad, teachers who would be encouraging, that made the difference, rather than someone to look up to.
Well, and Dr. Seager, I'll start with you. I want to ask each of you about how you connect presently or past to the Apollo program. Your memories of the moon landing, or if you're too young, your memories of learning of the moon landing. What's your connection to Apollo?
Yeah, well, I think I'm the most senior person here.
Okay.
So I was actually allowed to stay up late to watch the Apollo 11 landing, and I remember so I used to write long letters to all the astronauts on all the space missions and send them to NASA, to the Johnson Space Center, and I would always get a nice autographed picture of the crew back, and I thought they were reading my letters.
Yeah.
So that's
great.
That's basically how I started.
That's great.
I was born after the moon landing, but it was an iconic fact, actually, when I was, grew up and was able to pay attention to space science.
Yeah.
And I was a little bit too young to actually remember Apollo, but I will say when so I grew up in academia and then ditched my tenure to go join the government, worked at NASA for 6 years before coming back to academic institutions. And when I was considering this opportunity, my husband, John, who's sitting here in the front row, he was like, we're watching From the Earth to the Moon. Have people seen From the Earth to the Moon? Mm-hmm. The amazing HBO miniseries, docudrama kind of about the Apollo program. If you haven't seen it, it's online, go check it out. It's done incredibly well by Tom Hanks. And every night I would come home and say, we have to watch another episode. And it just got me so inspired about what was possible, because it was right at the beginning of us thinking again about what's going to be beyond the space shuttle and what can we do beyond low Earth orbit, and to have the opportunity to go and be a part of that. And looking back at how much work there was to do in those days of Apollo and how much innovation emerged from it really inspired me to follow that path and go and join NASA at the time. And I got the chance once in the basement and underneath the Smithsonian to tell Tom Hanks, you made it a great show there. Thank you so much. And I went to NASA because of watching your show about Apollo. And he was very cool. He's also short. He's pretty short. Oh. Okay. He was very excited, though, that somehow that influenced
We're answering
me.
all the questions. Great. Let's get into the weeds a little bit. Dr. Zuber, your focus is on the moon. Jim Lovell, played by Tom Hanks, he was asked late last year in an interview what NASA should do next, where it should go next. And he said, quote, "We know more about Mars than Neil Armstrong knew about the surface of the moon when he walked on it. We should go back to the moon." Do you agree? And if so, why do you think it's important to go back there?
So that's it's true. So actually when I think about what we know about Mars now, that I think we'll talk some about, when we landed on the moon, there were legitimate scientists at the time who thought that the lunar module would just sink into what they called foo-foo dust, okay? And that it was just all unconsolidated dust, and that the LEM would sink. And of course, there was the surprise when Neil Armstrong was trying to land and they were running short on fuel, that there was this crater there that they weren't quite expecting, and he kept a cool head. So we have samples from several locations, 6 Apollo locations, and I use the analogy sometimes. So imagine that you're an alien from another planet and you came and you landed 6 different places on Earth. Would you know all about the Earth? Mm-hmm. Okay, and the fact is you would know clearly something about the Earth, but there would be it would be very selective and very difficult to put together a big holistic picture. Okay, now we have so actually there've been the nations of Earth collectively have sent over 110 missions to the moon. Now, a bunch of them missed the moon, some of them crashed on the moon, some of them landed successfully, some of them orbited, and all of those missions have learned things. But every time we go to any planet, including the Earth, okay, and to a place we haven't been before, or we look at the same place with a different set of eyes, a different kind of sensor, it has never failed that we learned something really important. So you saw on the news within the last couple of weeks about a gigantic mass on the far side of the moon. That was actually my data, and my former student was the first author of that paper. And so we have flown over that area with various spacecraft many, many times, but we now had the right data set that tells us, okay, well, we may have found the core of the impactor that made the largest known impact crater in the solar system on the far side of the moon. So, I often get phone calls saying, what are we going to discover on your next mission? And I say, if I knew, I could have saved myself a lot of time. But I think it's fair to say, and it's not an exaggeration, that discovery is assured.
The moon mission, as you know, was also a very patriotic enterprise. I'm wondering if any of you want to talk a little bit about whether there's still a competition over space.
Absolutely. I think that there's a different global landscape now than there was during Apollo. Clearly, the US-Russian competition really drove, in many ways, that program. Now, I would say it's more, we're interested in what's happening in China. Obviously, I think, especially, I don't want to speak for my colleagues here, but as scientists, we tend to hope that we can do this all together, that we can do this multinationally and collaboratively. But the truth is that technology and innovation really does come out of these missions. The incredible capacity to manufacture, say, computers at scale came out of the Apollo program, right? All the chips that they made for Apollo, they made millions of them, even though they only needed a couple hundred of them. We didn't know how to manufacture computer chips at scale until Apollo needed them. These are things that really impact our economy, and you want to make sure that you're out there in the forefront. And so a little bit of competition isn't bad for that. It really drives us to keep innovating. I hope ultimately, though, the exploration and settlement of space will be done in a way that's cooperative. That's my perspective on it.
And I'll just add to that. So I agree. So as a scientist, I hope every nation's space mission succeeds because there's always more to learn, and we're not going to run out of things to learn because somebody else discovers something. We'll just go discover something different. But we collaborate very effectively. Many of my collaborators are international collaborators, and it's fantastic. But it certainly is true that being at the cutting edge of technology allows, gives you that different set of eyes that you need to stay a step ahead. So.
I will second everything they said, but there's just also a logistical challenge with working with people in other countries. Like, you're going to fly to Europe every week or Japan. It's just hard to work when you're not face to face and developing brand new things.
Dr. Leshin, let's turn to your specific field of inquiry. Sure. It's astrobiology, the search for life elsewhere. What exactly are you looking for? How will you know when you find it?
That's a good question. I was noticing what picture of my girl on Mars back here. That's the Curiosity rover on Mars. That's her selfie. She has a camera on the end of her arm, and she took her own picture there on the surface of Mars, and she's been roaming around there for over 2,000 days exploring this wonderful site, and doing so from the perspective of astrobiology. And so as we think about, and I'm kind of nerdy, but I think this is a really grand question, is are we alone in the universe? Like, is there a more profound question as scientists we could attempt to ask? And I ask that question from the perspective of the solar system and the planets in our neighborhood. Sara does it on a much grander scale, which she'll get to tell us about. When we ask that question about our own backyard, we literally have to start in our own backyard and ask, what do we know about searching for life elsewhere based on the history of life on our own planet? And there's some pretty simple truths that we learn when we study the history of life on Earth. And they are, one, it started really, really early on this planet. Like, pretty much as soon as something could come together and be alive, it was. Within the first few 100 million years of Earth history, it was alive. Over 4 billion years ago, there was life on this planet, which is kind of amazing because it wasn't a very pleasant place to live. The second thing we know is that we need that liquid water and an energy source. Life needs food, right? For us, it's cheeseburgers, but for life in the oceans, it could be other kinds of things, and even energy from eating things like rocks can work. And then you need the raw materials of living things, and most likely those are going to be carbon-based materials. So those are the kind of things we look for. So when we design this beautiful experiment on the picture behind me here, we're off looking for places where those ingredients came together, where there could have been liquid water in the past, where there could have been food, energy sources for a living thing, and where there were the raw materials. And that's what Curiosity has been up to on Mars. It's been looking for organic matter. It's been looking for water. It's been trying to characterize environments on this nearby neighbor world to see whether or not they could have been inhabited. And the exciting thing is, with that amazing set of tools that she carries around with her, analyzing, and this picture is actually taken at the very first place. We scooped up a dirt sample and fed it into the instruments in her belly and analyzed it, and I was able to analyze that there was actually quite a lot of water at the surface of Mars, which will be helpful when we send astronauts in the future. But we were able to learn that this environment she's sitting in is indeed a dried up lake bed. It was once a place, probably a few billion years ago, where if you were a bug on Mars, you would have been more than happy swimming around in that sea. Now, have we found evidence that the bugs were actually there? No. We know that we had all the ingredients. We still don't know whether we made the soup. And that's really the science going forward. So as we look to future missions, they'll still be trying to answer this question of whether or not life got started on Mars.
Well, we know that Matt Damon can start water, find water on Mars.
Yep.
So you're covered.
It's right there in the soil.
Send 'em up.
And that's good.
Okay.
You just got to mix in a little bit of your own organic matter, apparently.
Right.
To grow
I
your
saw that part.
potatoes. Yeah.
Dr. Seager, you're also on the search for another Earth. How hard is it to find exoplanets? What goes into that?
It depends on what kind of exoplanets. I just want to remind everyone that you look up at the night sky and see the stars, that all stars are suns. And our sun has planets, so it makes sense that these other stars also have planets. And it looks like every single star has planets, basically. And you look at the night sky, if you can go to a dark site, you'll see thousands of stars. But our galaxy has hundreds of billions of stars. And if every star has one or more planets, there's at least 1 trillion planets in our own galaxy. I mean, there's just so many of them. But unlike the moon and Mars, we can't send spacecraft there. These stars and planets are just so far away. So we use telescopes to look for planets. And there's many ways to find them, but the main way we do it now, I'm just going to take a second and explain it.
Yeah.
But some planets and stars, they're actually lined up just so. The planet is orbiting the star so that the planet goes in front of the star, as seen from our planet or our telescopes. And the stars, they're just points of light, but they drop in brightness by a tiny amount, by a percent or a tiny fraction of a percent as the planet goes around. And the planet will repeat every once in orbit. And right now we have an MIT's leading mission called TESS, like the girl's name, TESS, Transiting Exoplanet Survey Satellite. And although that mission costs a few $100 million, it's very excellent in finding planets. And so we're looking at large swaths of the sky, giant strips of the sky for 1 month each. And in that data, we have thousands to hundreds of thousands of stars. And our computers help here and at NASA help us find these little tiny drops in brightness. And we have many complicated computer algorithms, including artificial intelligence, which is our major buzzword in science today. And we find candidates. And once our computers have found all these little candidates, every Tuesday and Thursday afternoon, like a small group of people, mostly young people, sits around in a room, and we go through the ones that the computer was stuck on, and we look through them, and we have a lot of data, information, and we select out about 100 per week that go to the observers who are doing follow-up work to see if these little drops in brightness might or might not be planets. So every week, we're coming up with basically 100 new signals that may be planets. They're just everywhere.
It's sort of like an American Idol process of
Yeah.
seeing them come in and
Except there can
are they
be
going to
more
be
than one
stars
winner.
or not?
There can be more than
They're
one
all
winner.
winners.
Good.
That's right.
I want to go back to Mars for a second, Dr. Leshin. What, in addition to life, what other questions can we ask about Mars that will answer all hosts of scientific inquiry?
Sure. So, I mean, I love the did life ever get started on Mars, because it teaches us so much about, like, if we know it happened at least one place, although sometimes I question intelligent life on Earth, but that's another issue. But if it also started literally on the planet next door, wow, that's going to give us a lot of confidence that life is a bit like stars and planets that could be everywhere. That would be really exciting. But As a geologist, as a rock lover, Mars has all kinds of really fascinating things. The largest canyon system in the solar system that would span from Boston to LA. The Grand Canyon would just be sort of a wussy little side canyon on this canyon system. Volcanoes the size of New Mexico. I mean, enormous. So it's got big, big geology on Mars. We love that part. It also has, Maria can talk more about, things in the interior that are really fascinating. And with the mission that just landed there this past year, InSight, they're learning about the interior of Mars and understanding how it works as a planet. So all that science is really, really exciting. I think for me, though, right now, the really interesting thing, and the next mission that will launch to Mars, which will look a lot like that beautiful rover, because it's kind of the next generation of it, will launch next year. In addition to exploring more around the possibility of life and other scientific exploration of the surface of Mars, it will also be working to leverage the resources of Mars in ways that humans ultimately could, to figure out, can we pull CO2 out of the atmosphere and use it to make components of fuel, for example. So we're getting ready for humans. We're getting ready for people to go and be the next explorers on Mars. And robots are awesome, and nobody loves robots more than me, but having human explorers on Mars is going to be a complete game changer. It's going to allow us to do so much more, so much faster. And we have a lot to do to get ready. We can absolutely do it, and it's great to see us starting to use our robotic pathfinders to really pave the way for humans.
Well, I'm sure I'm not the only one. I'm really interested in whether there's life out there. Do you think I'll get the answer in my lifetime? Will we all solve this?
We're trying really hard.
Okay.
I'm optimistic. I think it's really achievable. Probably have to get a little bit lucky. It's, you know, like just like every rock you go out and pick up out here, it's not going to have an obvious fossil in it, right? So we gotta be a little bit smart and a little bit lucky. We're pretty smart, and then let's hope we get a little bit lucky too. But boy, I think it's really likely that it's happened, and so.
And you gotta, I mean, we know what Earth-like life is like, and so the question is, what are we looking for? So, so there's the idea of, you know, gases that are out of equilibrium, that there's a process going on, so we know to look for that. But there could be other things that we should be looking for that we don't yet understand, so we just got to be really open-minded.
What we are looking for, at least for exoplanets, is we're looking at the atmospheres for gases that might be produced by life. Like, we all heard of the rise in carbon dioxide. We're influencing that, but that is a tiny, I mean, it's a huge change for our planet's climate, but as seen from afar, that's quite small. We're looking for things like on our planet, oxygen that we all require to survive. It fills our atmosphere by 20% by volume. Without life on our planet, without photosynthetic life, we would, like plants and bacteria, we wouldn't have any oxygen. So like our life has re-engineered our atmosphere in a huge way. And so we're looking for these signs from afar using our space telescopes to see things that are unusual in the atmosphere. And like a forensic crime scene, we sort of have to pick apart the pieces to try to convince ourselves that we might be something indicative of life. So it's not, as Laurie said, the fossil that, wow, there was life. It's really complex and requires getting lucky and seeing the right signal and being able to recognize it when we see it.
I keep waiting for something to crawl by the rover. Hasn't happened yet. Has not happened.
Hidden camera.
Yeah.
As has been noted, I see some kids, teenagers, young people in this audience, which is great. Do you find kids, young people, are more or less interested in space? You remember when kids, you know, wanted to be astronauts. Is that still the case, or is now a time to really pull in the next generation?
No, it depends on the age. I mean, if there is an age where kids love space, they love dinosaurs, they're interested in everything, and then there's the older age when they get a phone, and then they, like adults too, right? Care about their phone and teenage things. So I really think it's still, the interest is definitely still out there.
Yeah, I'm super inspired. I don't know, what do you guys think? Do you like space? Yes, yes. Okay, we got some good. We got some cheers down here, down front.
If you study space, you never have to work.
Yeah.
Right. You know.
It's awesome.
You have to explain that. They didn't get it. I don't think.
It's awesome.
I feel like I've never had a real job. Right. My hobby is what I do.
Yeah. I think people are still interested. I think there's a lot more distractions now. There's a lot more going on, and I do think, you know, right now, not launching astronauts from U.S. soil is it's kind of throwing people off. And so I think once, you know, when people see a Falcon Heavy has launched, like the attention is huge. It feels like the old Apollo Gemini days. Yeah. And I think as we really start launching US astronauts, some space tourists, some private research scientists on these missions, people are going to get even more excited about them. But I'll say in the space business, I mean, whenever we launch a mission to Mars, whenever we land a mission on Mars, the attention is incredible. People are into it. And we're doing that more and more.
One of the differences for kids today is they're so connected to the internet. Like one of my friends, her 9-year-old once, they were on like a once-in-a-lifetime vacation to Wyoming, and the kid said, "Oh, stop the car now, let's go outside." He's like, "Oh, see that? That's the International Space Station flying overhead."
Right.
Because he had been at my house, and for my kid's birthday party, we went through some trouble to find out when ISS would be going overhead. And we saw it, and we knew where it was. We went out and waited, and it's like a bright star that acts kind of strange and goes overhead. But he had just sort of participated in that, but he was able to like look online and like try to Google something and figure it out. And so kids have more, not like every kid will go ahead and do that, but they have more, if they want to learn about the moon or if they heard the word exoplanet, they've got more they can dig into.
Even if you're into your phone, I mean, there's a lot you can do. So I can program, my instrument that's in orbit around Mars right now from my phone, okay, and track it from my phone. And also, I've got the gravitational wave app on my phone. So whenever there's a possible detection of a gravitational wave, I get a ping on it.
That's the one notification you have turned on, right?
And there's.
I have Angry Birds, but same.
The amazing thing is now all the data.
We'll set up your phone. We'll set up your phone for you.
Set me up.
Spotthestation.com, Spot the Station. Spot the Station is how you can find out when the station's coming over your house, and definitely check that out. It's awesome. But the other thing now is all the pictures are available a day of from Mars. That rover, you can go on, if you just Google Mars Curiosity raw images, you will find yesterday's pictures from Mars all online. And so that selfie, the picture that you saw behind us up here, that was the official NASA version. It's actually 72 or something images all put together from the end of her arm. But an amateur did it first. They actually beat us to it, because all the pictures were available for free, and they went out there in their software and they put it together, and it's so cool.
Yeah, and I mean, one of the things that I actually still, this never gets old, but when you go into the office in the morning, downloading the data that came down from space the night before, and now it's all out there, so as Laurie said, anybody can get it. But I never have and never will get over the thrill that for some amount of time, I know something that nobody else knows.
Yeah.
Okay? So it's the thrill of, there's a discovery in every image that comes down. And any of you in the audience could be a part of that discovery by just getting up and down.
For finding planets, for example, there's a website, planethunters.org, and they take real test data and they put it on this website, and you click through it. And it trains you initially how to look for a little tiny drop in brightness of a star that's taken an image as a function of time. And so many times, and who's on these sites? Sometimes it is a retired engineer, but it can be a stay-at-home mom, it can be someone who wanted to be, an astronomer, kids actually. Some times a 10-year-old will spend like a ton of time on this. And the public, everyone can contribute.
For any girls and boys who may be intimidated by the math and the science of space study, like I was, what other jobs are there for people who love space and who want to be involved in space, but maybe aren't the brightest bulbs on the planet?
We just wanted to say at the outset, though, we do encourage everyone, boys and girls, to work on math. Like in my family, it's not the math, but believe it or not, it's the writing. That's like a massive challenge. And so we encourage, try hard, school, elementary school, high school. It's really your main chance to get better at what you're weak at. So we want to send that message out there. Just get help with math, do as good job as you can. But all that said, all kinds of jobs. I'll pick some higher end ones like lawyer. We all need lawyers even at work. That's a good job, accountants. But even writers and people who want to make like a documentary or movie, or journalists, we need you to help us communicate the message about why space exploration is so exciting and why it's worth supporting. So there's so many jobs out there.
Yeah, absolutely.
And I would just say, you don't have to be a math geek to be involved in space. What I call, there are so many jobs for people who are, what I will say, STEM aware, okay, who know a little bit about math, or enough to use a computer, enough to use apps on a phone. There's just so many opportunities because there is a lot of canned programming. And so one of the things I led a mission to the moon where Sally Ride worked with me on, we put cameras on the spacecraft that middle school kids could program. And I would go to schools, middle schools, with the kids and sit down, and every single kid in the class could run the software and program and take their own images, because they sat down and they decided this was more fun than doing whatever else they could have been doing in school. But everybody has the capability to do that.
And I would just add to that as well. I completely agree. At WPI, the university that I'm the president of, we very much embrace this idea of project-based learning. So almost nobody, even us space geeks, like math the way math is often taught. However, when you get to apply it to something like taking a picture of the moon or helping people in a real community get clean water, and when you get to use engineering and science to really work in these very exciting and meaningful ways, you suddenly realize, hey, I can do this, and by the way, it's really important that I do this. And so I would just encourage people not to kind of buy into the I'm not good at math thing, because probably you haven't had to use it in a way that you really could succeed and make a difference in somebody's life. And so it is possible for absolutely anybody to be in these fields if you decide that you want to do it and get yourself in that right experience to be able to have that lightning bolt moment where you go, okay, I'm going to figure it out, whatever it takes, because it's so cool to get to do that.
And when pulling kids in, I wonder what your thoughts are on this. I was in school, again in Massachusetts, where a teacher was sent into space, and we watched it, Challenger. And that was obviously a seminal moment in not a great way. Yeah. And I think my generation really remembers that. Yeah. Then flip to a few months ago or last year, the decommissioning of Cassini, which I watched as well as an adult. And I was tweeting online hoping kids would watch that because it was just so cool. Yeah. How do you walk that line of getting people interested? You want them to see people going into space. Absolutely. But it's dangerous.
Yep. That's there are definitely risks involved. I mean, we really count on. We had the conversation this morning with the CEO of Boeing about the importance of safety, and nobody knows that better than companies like that. And but I have to say, when we're pushing boundaries, when we're pushing envelopes, there's risk involved. I think that the key for us is to come together across all sorts of types of backgrounds to understand what those risks are and do everything in our power to mitigate them and understand them walking in. And we learn things from every single failure, and we carry those things with us as we go forward. Yeah. The good thing about thinking about sending more and more people into space is it is going to become we'll get much more experience, right. And then we'll just get a lot smarter and keep getting smarter and keep learning along the way. But there's risk. There's risk in a lot of things we do every day.
Big dream of going to Mars. Like, who here would go to Mars if you could go? Like, everyone, most people want to go to Mars, but the risks are huge. Like, you've seen the movie The Martian, and that was a good ending. So we sort of have to weigh the risks against, what it's going to be. But yeah.
But great things only come if you strive,
right? But you can't get there without risk. So for example, in the commercial space field, I mean, there was pressure to apply kind of the same safety profile as we use in commercial air flight, okay? In which case there will never be commercial space. I mean, it should be more like extreme sports. So you should be able to accept a risk, the same risk that you would accept when you decide to climb Mount Everest, okay, which is risky. But if it has to be the same as commercial air flight, which is very, very safe, okay, you'll never get over the hump of getting to the next level.
And get the experience to learn. And are there going to be losses? There could well be. It's, I don't know, I just watched, in traveling this week, I was like stuck in airports for hours and watched Free Solo. Has anybody seen that movie?
Oh, yeah.
Like, okay, there's a bunch of crazy stuff taking place right on the planet, much less out there. So, look, if there's people out there willing to do that, then I think we're going to find a lot of people who are willing to accept some risk to get that amazing vantage point on our world.
I saved the most contentious and controversial question for last. What's your favorite space movie? And why?
Do you have a good answer?
So mine's The Martian, okay, and it's because scientifically it was really solid, okay, and the two places where it wasn't solid, okay, was first of all, they didn't deal with radiation. There is a threat of radiation, as was discussed, earlier today in the astronaut panel, and of course you can deal with it, but they just punt it on that. And the other one was that the Martian atmosphere is 6 millibars, and when the wind blows, it wouldn't blow a rocket over. Okay, and I actually had a discussion about this with Matt Damon, who when he gave the commencement address at MIT, and after his address, I was sitting there, and he was like, "Well, Maria, we had to strand me there, you know." I mean,
artistic license,
right? But the thing that I love about the movie is that the esprit de corps and the way that the people at JPL and all the other space agencies, the way they acted, that's the way those people really are. That there was, that wasn't even 10% exaggerated what they would do to protect a single person.
Wow.
Yeah.
My favorite movie has no scientific validity, and it's my current favorite is The Arrival, where you remember the big pods coming down, and the reason is because how many movies have you seen where it's the little green humanoid that comes to Earth? When you think about finding life elsewhere, it's the little green alien. But there, they gave us this notion that perhaps life elsewhere, intelligent life, is so different we could never conceive of it. So different. And that's what I like to remind myself daily, that the life elsewhere that we're looking for, we won't see it directly. We'll just see the gases that the life breathes out. But we have to really keep our eyes open and our mind open.
Yeah, so I too like the movies that are realistic about space. So my favorite is Star Wars.
Totally happened.
I think it's really happening out there right now. We just can't quite perceive it. No. So it's that same time of life for me as I was seeing those Martian rocks and wanting to reach out and touch them. And my dad was taking us to the Grand Canyon, and he also took us to see, in the middle of summer in Phoenix, where I grew up, and I was standing outside in the middle of July in the huge long line that was there for all those Star Wars movies. And it being so crowded that we had to sit in the very front row of the biggest theater in Phoenix, and it was so loud that we took popcorn cups and put them over our ears because it was like, oh my God. But I was transfixed, and I have been ever since, and every time it's on TV I watch it because I just can't help it, and I can say all the lines. And it's a fantasy, but it's one about sort of the classic human story in space, and I love the idea of bringing the human story into space.
Well, I have to ask you just while I have you. Mine is Contact.
Oh, good one. That's on the list.
I entered Cornell a year after Carl Sagan died, where he was a longtime resident professor. I need to know from all of you, Contact.
Yeah.
Could it happen? Is there someone at SETI listening to
Yeah, definitely.
sounds from Vega?
Yeah, absolutely.
Also now there's a kind of new SETI where we know the stars with planets.
Right.
And part of SETI activities are focusing on stars that we know have planets around them. But SETI has seen a resurgence lately. They've got new cash flow, and it's kind of coming alive again in a bigger way. SETI will tell you in the search for purposeful radio signals from an intelligent civilization, they'll tell us that they've searched the equivalent of 1 glass of water compared to all of Earth's oceans.
Wow.
So there's a lot of real estate out there.
Yeah, and this is another one where you can get online and get the data and look at it and analyze it. So you could discover this.
Amazing.
Yeah, Carl Sagan told me when I was thinking about going to grad school, I was thinking about going to Cornell, and I actually met with him, which was like, are you kidding me? And
Wow.
he said I'd never make it in the space business, so. Because he thought I wanted to be an astrophysicist, and I wasn't a physics major. He didn't really get what I was going for as a geologist, but I was like, I called my best friend, I'm like, Carl Sagan told me I sucked. It was awesome. Oh my God. So don't always listen. Don't listen to the critics. Don't listen to the critics.
Well, I just want to thank you all so much. This was an incredible opportunity and incredible to just sit down with you and ask all the questions I've wanted to as a frustrated space nerd my whole life. I really, really appreciate it. And thank you all.
Thank you so much. Thank you.
Thank you. That was extraordinary. And if you should happen to find another asteroid and you don't know what to name it, perhaps Kennedy. Just saying.
I'm working on it. There's rules about political figures, unfortunately. So I'm working on it, though.
So if you are joining us today, I encourage you to also visit the Space Summit Expo, which is set up in the library's pavilion for a little while longer. We also have space-related items in the bookstore. If you like the programming and mission of the Kennedy Library and Museum, I would recommend that you join us and text JOIN JFK to 44321 and become a member. We'd love to have you in the family that way. And if you're joining us for any of the other panels, please bring your tickets, and tickets are required for re-entry. Again, thanks to our panelists. Terrific. Oh, I love it. And we continue with the Space Summit.